Hello, everyone. Welcome back. So let's keep going here on chapter 9. We're almost done with chapter 9. The last part of chapter 9, we're going to talk about shapes of molecules. Okay, so we talked about last time Regin structures. So it's important that we can draw Regin structures and then assign partial or formal charges to predict which one is the most favorable. Okay, but in discussion this week, we will go into all about how to draw good Regin structures. So I'll give a little mini lecture in discussion this week. Okay. All right. So, there's a lot of different ways to draw Regin structures, and depending on who you ask, there's certain rules that we should try to follow based on experiment, chemical reactivity, and things like that. But if we don't have conclusive data, and there's nothing wrong with drawing a structure that obeys the octet rule. Now, and sometimes we can draw structures that don't obey the octet rule. So, in my opinion, I don't mind what way of thought you think about these structures. If a atom can expand its octet, you're perfectly fine to draw and pass an octet. But you're also fine if you want to leave the atom as an octet, and we'll go into what we mean in discussion and also today. Okay. So let's take the example of SO2. We can draw SO2 as the left structure, structure 1, where all the atoms have an octet. And then on the right structure, structure 2, all the atoms have an octet, but you see sulfur can expand its octet. So the formal charge of sulfur is 0. Okay. So let's calculate the formal charges on sulfur. Let's circle our sulfur atom here. Let's use a different color so I can differentiate from the black color that's in the text. Okay. So sulfur, remember our rules for formal charges. We take the group number or valence electrons from sulfur, and from that we subtract all the electrons that are in the circle. Since we bisect these 3 bonds, that's going to be 3 electrons. Because it's a bisector, we break the bond evenly in 2, then minus 2 for the lone pair in the circle, and we get a charge of +1. Formal charge of +1. In this structure, we get 6. Circle this sulfur atom. We get 6 minus 4 minus 2. So that gives us a charge of 0. So we have +1 for structure 1. And then structure 2, we get 0. So which one of these structures is correct? Well, there's not an easy way to answer that question. You need data. You need data from experiment. Okay. Well, in this case, since this molecule is well known, we have studied it since old times. So, in one study, using additional multiple bonds and expanding the octet around the central atom, it may not be the best representation of the structures of many molecules that have been drawn this way. So this is why I say as long as you have an octet, you're okay. There's nothing wrong with having formal charges in the molecule, but the rule of thumb is the best Lewis structure is when there's no formal charges at all. But if you kind of think about the structure as a whole, sulfur is not very electronegative. So the oxygen atom, one of the oxygen atoms wants to take electrons away from it. So it's more likely that the oxygen atom will have a negative charge, a formal negative charge, and the sulfur will have a positive charge because it's next to the oxygen atom. So you can think of it like that as well, but you don't have to. Okay? All right, let's move on here. I don't know why I selected this, so let's cut that. Okay. In this class, we try to use expanded octets. So an expanded octet is when you have more than 8 electrons around an atom. So we try to explain the bonding in structures with more than 8 valence electrons around them. So like if something needs 8 single bonds, we're going to put 8 single bonds because that explains the valence electrons around the central atom. And then to determine how many bonds we draw, we use a formal charge as a tool to determine which is the best Lewis structure. But in this class, we should not expand the octet for an atom for the only purpose of minimizing the formal charge. So for example, if you expand the octet to go from +1 to 0 in the case of sulfur that we just looked at, you should not do that, but I won't look down on it. So if you do that, that's perfectly valid. I just want to get people thinking that that's not necessarily a thing we should do because it doesn't necessarily reflect the chemical properties of such compounds. So it might not be reflected in actual data. Okay. So in my view, I like to describe sulfur as structure 1 rather than structure 2 because it kind of shows you that it has resonance involved. Okay, structure 2 is kind of like a hybrid of the two resonance structures. So that's why I don't particularly like structure 2. But it's okay if you draw that. All right. So now let's talk about shapes of molecules. So the electron domain model. So the purpose of this this lecture, if we go back to the title of the lecture itself. Well, I didn't put it. Sorry. It's going to be Lewis structures part 1, and now we're going to talk about how we predict the shapes of molecules. Okay. So if you remember kind of in maybe old chemistry classes, but it's okay. We're going to go over it again. The shape of, say, a molecule can be determined by using what we call VSEPR theory, or valence shell electron repulsion theory, and it's called the VSEPR model. So it sounds like Vespa, but it's VSEPR model. So in these days, we refer to the electron domain model, where we look at the central atom and we count how many electron groups or domains are around it. So electron domain can be either a lone pair of electrons or a bond. So a type of bond, a single, double, or triple bond. So double bond counts as one domain, even though there's 4 electrons in the bond. And then a triple bond, even though there's 6 electrons in the bond, it still only counts as one group or domain. So common mistake students make is that if they see a double bond, they count that as 2 groups, but it's only one because there's only one type of bond between the 2 atoms. And then each electron domain, you count them separately. So a single bond, a lone pair, that will count as 2. And then you have 2 lone pairs and a single bond, that's going to be 3. And then you have all bonds, that's 4 bonds, 4 domains. And you have 2 lone pairs and 2 bonds, that's still 4 domains. You have a double bond and another double bond, that's only 2 groups, so that's 2 domains. And the variations can go on. All right. So the most the kind of the introduction to this is we have 2 domains. You'll get a linear compound like we see here, 180 degrees. So the degree represents the bond angles between the spheres. So you have only 2 domains like CO2. That's going to be a linear compound because it only has 2 electron domains. So only 2 atoms around the central atom, 2 domains. 3 domains like formaldehyde, boron trifluoride, their bond angles are 120. And then 4 domains, we have 109.5 degrees. So that's between each of the atom spheres there, 109.5. Okay? So this little tidbit here, 2 domains will take up positions on opposite sides of a central atom. And that's because that minimizes electron repulsion. So think about the electron groups, right? They're electrons, so they want to spread as far apart from each other because they don't like each other. They're kind of they have the same charge, right? So yeah, they both have too much energy, right? So they want to be as far away as possible to make the whole molecule stable. And same with 3 domains. Get as far apart as you can, then 4 domains, etc. So these shapes often refer to shapes you see in geometry. 2 domains, a line. 3 domains, a triangle. And 4 domains is a tetrahedron. So a tetrahedron is basically a 3D object where all the faces are triangles. So it's like a pyramid, but usually pyramids have a square base. Okay, so let's go over some of the shapes here. So linear, 2 domains. A fine example is beryllium hydride, or beryllium hydride. Another example is CO2. And you see when we draw the oxygen atoms here, they are the molecule looks very similar to beryllium hydride right there. So the molecule is 3D, but what is the shape for this molecule? So we call this linear. So there's 2 names we can think about. There's electron geometry. So in this case, we have electron geometry. So electron geometry refers to how many electron groups are around the atom, regardless of whether or not they are lone pairs or not. So electron geometry, that's the number of electron groups. So in this case, it'll be linear. And then molecular geometry is the actual shape of the molecule. And the electron geometry will change depending on if you have a lone pair or bonding electrons. So in this case, since we all have bonding electrons around the carbon atom, this is also going to be linear. And we'll go into the different flavors of this later on in the discussion here. Okay, so that's linear, and that's for beryllium hydride and carbon dioxide. All right, so now we get into 3 electron groups, 3 domains. So here's one example, boron trifluoride. So boron trifluoride has 120-degree bond angles. So we call it trigonal planar because it has 3 points on a plane. So if you drew the edges here, you see it represents a triangle right here if you connect all the dots. So it has no 3D character, so we usually don't write bonds with 3D representation here. It's a flat molecule, so we call it a 2-dimensional molecule. Only has the x and y axis, or x and y coordinates. Okay. Let's compare now this with formaldehyde. So boron trifluoride has equal bond angles of 120. So that's the classic example. Now, if we could deal with formaldehyde, we see that the oxygen, the carbon in the center there, has exactly 3 bonding groups. Oxygen double bond to oxygen, and 2 single bonds to hydrogen. But you see here the bonding angles, they're kind of not equivalent. They look close to 120, but they're not. And the reason is that the bond lengths in formaldehyde are not the same. So that's why you see that the oxygen, since it's a double bond, those electrons are going to be closer to carbon. And it's going to push the electrons from hydrogen further away. So that's why it tends to depress the bond angle between the hydrogens to make room for those extra electrons in the double bond there. Okay? So that's one more example of trigonal planar. All right. So if we have an example like let me see here. Which one should I do? Right, so let's go back to sulfur dioxide again. So let's look at this resin structure for sulfur dioxide. Okay. So what's the electron geometry for sulfur? So if we look at the electron geometry, we count how many electron domains are around sulfur. So we count the single bond. So the single bond plus double bond, single bond plus double bond plus the lone pair. So that gives us 3 bonding domains. So this is going to be trigonal planar. Now, how about for the molecular geometry? Well, it doesn't have all bonding electrons for the domains. So there's 2 bonds, 2 bond domains, and 1 lone pair. Okay? So when we have that, we don't call that trigonal planar no more because we have a lone pair. So we call this bent. So the shape is bent. And you can see why, right? Because it looks like the sulfur, the lone pair, is bending the angles from a linear shape. And it looks a lot like water now, right? For its bent shape. So we call that bent. So I'll go over kind of different flavors as we do more examples of this. All right. So that's an example for sulfur dioxide, where we have 1 lone pair instead of 3 bonds, 3 domains that are all bonds. Okay? All right. So let's go over tetrahedral here. We have 4 domains. The classic example is methane. You see here it represents a tetrahedron where we have 4 faces that are triangular. And the bond angles here are 109.5 degrees. So they're not 90 degrees. We can stretch the bonds, so they're approximately 109.5 degrees. Okay? All right. So in this case, for methane, for this one, the electron geometry is tetrahedral. And then the molecular geometry is also tetrahedral. Now let's imagine that now we have, instead of carbon in the center, we're going to have ammonia, where we take one of the lone pairs, we take one of the bonds from hydrogen and make it a lone pair on nitrogen, okay? So this molecule still has the same electron geometry, 4 electron groups. So electron geometry is still tetrahedral. Okay? But now its molecular geometry will change. So it has 3 bonds, 1 lone pair, and this is actually what we call trigonal, because it has 3 bonds. It looks like a triangle. Pyramidal. So we call it pyramidal, or you could call it trigonal pyramid, or you could say pyramidal or pyramid. Okay? So the reason we call it pyramidal or pyramid, if you didn't look at the structure for the nitrogen, right? It looks like a pyramid if you were to draw in 3D shape. So it kind of looks like a pyramid. So that's why we call it pyramidal. So that's trigonal pyramidal. Now let's do one more example. Now we have 2 lone pairs instead of 1. So now our classic example is water. Very similar to sulfur dioxide we just talked about. So the structure of water is very important. And it's because its structure gives rise to its unique properties. So all these molecules, water has the least number of atoms compared to methane and ammonia, but it has the highest boiling point. Ammonia is a gas at room temperature. Methane is a gas at room temperature. And water is very polar. It can dissolve a lot of compounds, so it has very unique properties, and one of the reasons is this unique polarity and its unique bent shape, which is optimal for what we will talk in chapter 11 for hydrogen bonding intermolecular forces. But anyway, for oxygen, its electron geometry will always be the same as the other two because it has 4 bonding domains, 2 pairs of electrons and bonds, and 2 pairs of electrons as lone pairs or unbonded. So it will be tetrahedral still. But now its molecular geometry is a little bit different. So for molecular geometry, we look at, now it has 2 lone pairs and 2 bonding pairs of electrons. When we have that scenario, we call this bent. So it has 2 bonds, 2 lone pairs. So this is what we call a bent geometry, and it makes sense because the water, it has 2 lone pairs and the molecule looks bent like it did for sulfur dioxide. Okay? So that's all the flavors for tetrahedral. You have either all bonds, tetrahedral, 1 lone pair, trigonal pyramidal or trigonal pyramid, and then equal amount of lone pairs and bonds. That's a bent structure. Now we could have 3 lone pairs and just 1 bond, but there's no compound that actually displays that kind of arrangement, so we don't have a name for it yet. So, but these are all the flavors of tetrahedral. Okay. All right. So that will be it for this video. I will pick up where we left off, and we'll talk about 5 domains in the next video. So I'll see everyone then.